Okay, we're off and running. We're going to try to mostly wrap up binary trees today. Our topic is about balancing. So the code is going to get a little deep and complicated today. This is probably some of the most gnarly code, but you're not particularly responsible for all the code we're going through today. As usual, it's more about the algorithm, but the code, I think it's good to see it working in code. And it's a little complicated. I actually found a crash bug in my solution code today. It's been around for a few years, and I hadn't run across it somehow. So it's definitely real code that we're dealing with, and so it's nice to kind of appreciate that complexity. Let's talk a little bit about what's coming up. Let's see. Let me hide this messy stuff here. Quiz 4 is available. I think I'll double check. It's not going to be graded, so it's going to cover lectures 12, 13, and 14. It's a good practice warm up for the midterm when you get a chance to look at it, because the midterm will be drawn in part from quiz 4. So take a random sampling of, the questions or some of the questions from quiz 4, quiz 1, 2, and 3 as well. So you don't want to forget about that one, even though you don't have to worry about a grade on that one, because that's an ungraded quiz. So it will cover performance analysis, some of our lecture today, a little bit from 12, since you guys are already looking at a lot of stuff with quiz 3. So just a heads up on that. By this Saturday around noon, I will have a midterm practice exam for you. It's going to be familiar because it's drawn from quizzes 1 through 4, but you'll at least kind of see what questions I'm targeting, and you can go study those if you feel like, there's an area where you're less comfortable than before. It's going to be about 50 questions. The practice exam, there won't be any corrected answers. So you just will at least get a sense of what the questions will be like. And it'll be timed just like the midterm for Thursday of next week. So you get a sense of how long it'll take. So that will be out there for you by this weekend. We'll have a full review on Tuesday. It's a little dry. Not everybody is that interested in the full review. So if you got to prioritize and spend your time on other midterms for other classes, you're welcome to do that. But I will be going through everything on Tuesday, like I usually do, just so you get one more look at everything. But it's going to be a little exhausting. So just prepare yourself. Now we have 8 homeworks this semester, so you get to drop one of them, or we drop the lowest grade. This is what I do in all of my classes. So the truth of it is you can skip any homework you want if you need to. Homework 4, though, is kind of set up as a longer term project. So there's 4 options out there. Oh, gosh, looks like I didn't update my slides. That's such a bummer. So these links right here, you'll want to go to Canvas and don't use those links there. So it looks like I've got a slightly older version of my lecture for today, but I'm just going to power through it here. So these are your choices, A, B, C, and D, for just open-ended or slightly more open-ended fun problems. They don't relate to a specific algorithm, but like the vacuum cleaner one is kind of fun. You got to vacuum up a room with debris everywhere, and you could choose lots of different algorithms from stuff you already know, or stuff that's coming in the next couple of weeks. There's just kind of open-ended problems, and if you just kind of want to load up a binary search tree and implement that based on all the stuff we're talking about, because that's so kind of canonical. Like if you're going on to do other computer science courses, you might want to focus on the binary search tree a bit more. Then you can kind of tackle that one. That's kind of what we have coming and again, those are not really due until the end of the semester, so you can kind of work on it a little bit or look at them and decide which one you want to do, if any, and hopefully have some fun with that. So we've had a number of interesting vacuum cleaner implementations, and that's probably my most favorite one, but these other ones are pretty good as well. So next Thursday is our midterm. We'll have our review on Tuesday. You'll have your practice problems. The time test goes from, oh my gosh, this is out of day two. This is going to go from 5 o'clock to just about 8 o'clock. So 5:10 till 8 o'clock. It is our normal class time. It's 170 minutes. So just come into class as usual, and everything will be pretty automatic. You don't want to miss that. Oh gosh, it's 22.5. So I've got some pretty old slides here. I may pause and upload these again. So it's 22.5% of your final grade. So you want to be heads up on that. About 50 questions, multiple choice. So if you've taken my classes before, you kind of are familiar with how I kind of run this stuff. So that's what you got coming. So I'll probably pause here and upload my slides here in a second after we get through the introductory stuff, because I'm looking at a slightly old version here. Questions on the midterm? Okay, we'll cover it again on Tuesday, but it's open book. That means you can use reference stuff. You can search, just no AI conversation stuff. I think you'll see from the quizzes, it's pretty much, plug and chug kind of stuff. Just checking to see if you guys were paying attention, a little bit of code reading, things like that. But we'll dig into that more for next week. So let me actually pause our recording here. Sorry to do that. And then I'm going to swap slide sets here. So I'm not really kind of dealing with an out of date slide set. So give me just a moment here. Okay, we're back. Hopefully I didn't butcher things too badly. Okay, so for today, we want to just quickly touch on some homework 3 insights. I know folks are still finishing that, but this might be helpful. But since everything's fresh in your mind, it'd be good to cover that briefly. Introduce one of the 4 homeworks in case, so you can get a feel of what we're talking about. Quick slide review, and then how to delete nodes from a binary search tree. This is the messy part. So deleting stuff from a linked structure with pointers is tricky. And there's no way around it. You got to do with some pointer fix-up. So we'll look at how I do that in the implementation we have been working on together. And then we'll introduce concepts we need for balancing. So balancing a binary search tree is an important action we need to take after we insert or delete something from the binary search tree. One of the things we need to know is how far is it from any node all the way to the bottom. Boy, we're having a lot of ghosts in the room today. Hold on, let me just turn that guy back off again. So we got to actually search all the way from the current node to the bottom. So we'll look at that as max depth, and then we'll look at how we use that to rebalance a tree. So this is quite a juggling act, rebalancing trees on the fly, but it was invented quite a long time ago and is still really kind of one of the main ways we store information that's sorted, like a dictionary or something. It's quite an efficient way to go about doing it. So we'll look at things like balance factor and depth, and just kind of define those terms a little bit for you. And then we'll look at something, tree rotation. So this is really almost the end of the line for us with binary search trees. How do we rotate the branches in the tree around to fix it up when we break it? So these things are quite effective once you know how to actually use them. We're fixing the branches locally without rebuilding the entire tree. So this is a pretty advanced thing that we're looking at, though. And so once we throw all those things together, that's called an AVL tree. Those are the initials of the computer scientists who invented this back in the early 60s. And there are a couple other kinds of binary search trees. There's one called red-black trees. That's pretty common. They also deal with balancing, but they do it in a slightly different way. So we're specializing on one called the AVL tree. It's one of the earliest forms of the binary search tree. But before we dive into that, let's talk about homework 3 insights, this idea of a lazy push. And we're going to be talking about this lazy versus eager algorithms as we go forward. This is these 2 descriptive terms are standard terms used to describe algorithms. Lazy is a way of saying, well, we'll fix things up later on. So the lazy push is really just about sort of pushing something in at the top of the head and worrying about the pop later on, right? So there's our head with a push 1. So that's our maximum node pointer right there. We kind of know by definition that that's the maximum node pointer. When I push a 9, I can always ask myself, hey, did I just push something bigger than the maximum node's value? And so now we can kind of refer back to that max node and then update a pointer. So this is a nice little trick of just keeping a little extra pointer around so you know and don't necessarily have to go searching for the max node every time, right? So if we keep that, around, then we kind of always know where to go to do our pointer fix up potentially, right? So it's helping on the pop strategy if we know where that thing is, okay? So that's kind of our lazy push though. We stored a little bit of information, but not too much, okay? So now if we want to pop at the head, for example, and this is kind of the assuming or popping the max at the head of the list. This is assuming we have the max at the head. Now that's not what we did here, or actually, did we? Remembering value on lazy push. Oh, 19614. So it just turns out that I inserted them in a particular order here, but it wasn't that I necessarily was doing an eager push. So here, if I wanted to pop, right? So all we've got to do, and we've seen this before, is just say head equals head next if our max node is at the head, right? So, and then we can delete the max node. And that's the easy situation, right? And then otherwise, right, we've got to go, and then after that, we have to go through and we have to find the maximum value. Okay, so we're going to go searching, and it could be anywhere in our list, right? So we have a temp. We'll basically say keep going, and we'll keep track of our max head value. So if the temp value is greater than the max node's value, then we'll go ahead and remember the pointer to that node so that when we're done, we now have an updated max value, okay? So we're not saying that the max value is at the top. We're just saying we always kind of know where it is after we do some kind of a delete. So it gives us just a little extra information. If you didn't save this, well, then you're going to have to search for this in a linear way. It's not the worst thing in the world, but this is just one optimization you could actually take on this if you wanted to do that, okay? And then we have to update our max node pointer after each pop, right? So worst case, we gotta do n seeks to find the max after we do some kind of a pop on that, okay? So just a different way of looking at it. It's not the one and only way and may not be the most optimal way, but it's just one way. Now, if it turns out that the max node is in the middle, what do we do? So often what we want to do is kind of search and keep going while temp next is not equal to the max node pointer. So we're basically saying, hey, if I get to the node before the max node pointer, then I should probably stop because I'm now on the node that I need to use to remove max node, okay? So I'm comparing addresses here and saying, hey, if this arrow is the same address as this arrow, then I'm one before the thing that I need to cut out. So now all I got to do is just sort of kind of do a little pointer fix up there to say, okay, well, one, I could say swap value. So this is a trick we do from time to time, right? Sort of move the 9 to the top and then pop that thing off the top, okay? So, and you can do it recursively if you want, which is kind of a clever way of doing that, okay? But the key takeaway here is maybe tracking the main pointer to the node that we want to remove there, okay? And using our while loop to search through until we kind of stop at the right location, okay? And then we can kind of do our update. So recursive call pops the head and updates the max node pointer, which is pretty cool. So some of you were curious about doing this in a recursive way, and you can certainly do that if you wanted to, okay? So that's just a little look at that. If you're not done with this yet and you're really still kind of, with rough code, you're welcome to take this as a hint and then take it the rest of the way. Many of you, I think, have already probably got your solutions in hand, but I just wanted to put this out there for folks that were looking for a little help to get over the line there. So any questions on that before we kind of move on? Okay. All right. And again, there's more than one way to do that. All right. One example, just a peek at one of our homework 4 options is robot vacuum. So the idea with robot vacuum is you've got an array. It's a 2-dimensional array. So, and you've got some function calls that you're going to use to move your robot around. So you've got garbage, which is an obstacle. So the star is our obstacle and the dot is our garbage. So we want to go through and try to vacuum up all the garbage without vacuuming up any of the obstacles, of course. And our goal is, as always, efficiency. So we want to see if we can do this in a way where we do as little backtracking as possible. Because obviously, once you vacuum up something and you got to back the vacuum up, you're going to have to, waste some energy. So finding a way to do this really efficiently is a fun problem. You could do it with Brownian motion, right? You could just randomly move your vacuum around and eventually you're going to get everything cleaned up. Or you could try to go along the rows and then reroute yourself. But I'll kind of leave you with that for now because we're going to explore some interesting approaches that might make this thing relatively easy to process if you think of it maybe like a graph, a network graph or a tree. Okay, so I'll leave that with you for now. We won't dig too deep into that, but that's the kind of problems I want to put out there so you can have some fun with that if you want to tackle that. I always love kind of playing around with that one and have come up with my own solutions to that over time. So take a look at homework 4 on Canvas. You'll see all the links are updated there now for all of these 4 different types. And we'll introduce each one of them gradually as we go through the next couple lectures so you get an idea of what's out there. Okay. So quick review stuff. Don't forget, especially with the midterm coming up, you might want to jump onto Quizlet and just kind of review some of these sets. And we're going to talk about deletions and I think we did the min-max stuff already, but the deletions and the traversals will help you a lot. Okay. Again, your quiz 3 tonight, none of our lecture today will be on there, but it'll be on quiz 4, which is ungraded. Now, we said this last time. How do you know how deep something is in terms of N? Why do we care? Well, it's just kind of an interesting question to ask. And if you don't have a perfect tree, then you might need that ceiling function to kind of figure out what the answer is. But what I'm really getting at is I would like to be able to ask you questions like this. Sorry for the bright lights. You enter a binary cave system with 31 rooms. Every chamber leads to exactly 2 or more chambers, unless it is a dead end. How many rooms do you need to visit to reach the furthest dead end? Okay. Now this is a full cave system here. I didn't bother to do all the arrows, but this room leads to this one and this one leads to this one. So it's a classic log base 2, and we can apply that formula to get to an exact answer on that if we're dealing with a tree that's not fully fleshed out, okay? But that is mostly balanced, right? Assuming that we're more or less within balance, okay? So that's the purpose of kind of going over that. You'll probably see some questions like that at some point, probably more likely on quiz 4, but heads up for that when you get a chance to take a look at that stuff, okay? Last time we also looked at floor. So remember, the floor of a particular target value is what is below that target value. So if I'm looking for the floor of 7 in a in order traversal, that's going to be the 6. Okay. If I'm looking for the floor of 10, that's going to be the 10. If I'm looking for the floor of a 0, that's going to be undefined, right? Because there's nothing below the 0 there, and we don't have a 0 there in the binary search tree. Okay, so these terms are kind of hard to remember, which is why I kind of highlight them here. Okay, they're pretty standard terms. Ceiling is, of course, just the opposite. What's the next thing above it in the in order traversal of the binary search tree? And for us, the undefined for the ceiling would be if it's beyond the largest node. stored in the binary search tree so far. Okay. So those are our floor and ceiling, which are good to know. And then when we did insert, I won't drag you through all the code, but remember, if we've got a node 37 and I'm trying to insert some value X, the question is, well, is it, less than or greater than 37, right? And so now we start our traversal and we say, okay, well, if 37 has no left child, that's easy. We just create a node and plug in that X there in the lower left and everybody's happy. Otherwise, if there is something there, we got to recursively reevaluate because we have to go left. And so the 32 then becomes kind of the next level of our recursion that we go down and we repeat the process. Same thing on the right side. If there's no right child, plug it in because we're trying to insert. Otherwise, keep going recursively until we find a place where we can plug it in. Okay. So we covered that last time, and we won't go through that code again for that. Okay. Insert sorted kind of. Let's see. Why can't we increment the node count? Let's see. We have to recurse, right? Okay. So here's just a quick view of the code. I really don't want to go through this in great detail because we covered it last time, but it is kind of going to be on your midterm, so it might be good to just know that it's worth refreshing on. Okay. So there's the easy case, right? There's the recursive case, easy case, recursive case, just like we saw on the previous slide. Okay. So take a look at that if you need to dig into that again. And that takes us to our topic of the day, or one of them, which is deletion. So this is a little bit of a gnarly beast. So deletion of a node, assuming we can find it, right? So we have to try to find it first and then delete it. So if we find a node, it's not very helpful just to know that it's there. It'd be nice to have a pointer to the node, kind of like that max pointer we were looking at the beginning of the lecture. So first we try to find a pointer to it. And if we find it, we want to remove it and replace it with what we call a successor, if there is a successor. So a successor can be defined in one of two ways. We'll show you here in just a moment. Okay. But above all, we can't break the binary search tree. We have to maintain, less than or duplicate nodes on the left and greater than nodes on the right. Okay. So, and every subtree has to, maintain that as well. Okay. So we don't want to break that. So let's take a look at finding 21, right? And so one idea people have explored is what we call tombstones. And we will use tombstones again when we get to hash tables. But the idea with a tombstone is, as you might expect, you just sort of mark it as not being valid anymore. So we just leave it there. It's kind of the lazy approach. And then we just kind of skip over it if it's deleted, if somebody asks for it. So it doesn't really cost us much to delete it, and it doesn't unbalance our tree, but it can lead to some very unnecessary long branches after lots of delete and subsequent insert operations. So it's not ever really viewed as an ideal situation for a dynamic storage structure where things are going to get deleted and things are going to get added again. But you can do it as a shortcut. Okay. So, but we do pay a cost for traversing those nodes. So tombstones are never really a great idea. Okay. But turns out that there are some easy cases. So case number one, if the node that we happen to be deleting has no children, then we just need to fix up the pointer of the parent's right child. Okay. So if we're being pointed to by something, it's stored as a data member of this node here. Remember that every node has a left and a right node. So if we could somehow reach back and nullify that address for this node, we're kind of done, right? We ideally want to also delete this one, but we got to go back to that pointer right there and set that to null somehow. And if we don't have double pointers in our binary search tree, that can be a little tricky. Some of you have kind of experienced that in working through your linked list for homework 3. So, but assuming we know how to do that, then it's really just a matter of getting rid of that thing and fixing the pointer. Okay. And we'll go through the code to do that here in just a minute. So that case is relatively straightforward. So that leaves us to this case. So I want to delete 21. 21 has only one child. So in that case, it's similar. Rather than setting this thing equal to null, what I want to do is somehow set that equal to what the 21 is pointing to, and then get rid of the 21. So I kind of want to wire around that thing, right? So that's essentially all we're doing there, right? If we can do it, if we can fix that thing up, if we can get at that pointer, then that'll kind of route around the 21 and we can delete that node. And we haven't broken the binary search tree in any way. It's still a valid binary search tree, okay? So everything is still less than 13 or greater than 13, just kind of works out that way, okay? So that's the one child case, okay? Now, if something has two children, right here, let's say the 9, we want to delete the 9 from this tree. Seems kind of messy. But because of the way the binary search trees are structured, the 11 is really the successor to the 9. It's the smallest value on the right side of the binary search tree. If you remember, we said, we could hop right and then recurse as far left as we can go, and that's always going to find the minimum on that right side. So that's our successor. So what we want to do there is find the smallest value, and then we want to swap those two values. So we still got the node down there, but we've moved the 11 to the top and moved 9 into a position where it's a little more straightforward to delete the 9, okay? So this swapping game, as we saw with our binary heap, is kind of a familiar trick now. It's a great way to, get around a problem. So once we've swapped the values, now we can apply our previous rules for deleting a node that has only one child. So this pointer here needs to be updated to be what this pointer value is, so that effectively we end up pointing at the 12 here. And then our tree stays valid, okay? So now we can just delete that node and then fix it up. And we're back to a normal binary search tree. The 12 is greater than the 11. Everybody over here is greater than the 11, basically, okay? So that's the strategy we want to use. And, we could take one of two cases. We could sort of look to the right side to find the smallest thing as a convention, or we could look to the left side to find the greatest thing. So it's really just depends on, what standard we want to use in our delete code. So our alternate approach is sort of looking for the maximum one. Now, we're not going to really use this, in our quizzes. I'll make it clear that we're going to kind of be looking for the smallest one on the right. But the strategy is more or less the same, right? We're going to swap the values and then do the cleanup to get rid of that thing. And now we're back to a valid tree again, okay? But that's the idea for deleting these nodes. And even if we were deleting something here, the strategy remains the same, right? Find the largest or smallest thing on this side and then swap and do the fix up, okay? So that's the takeaway from this part of the lecture, is the strategy for finding the smallest on the right side, swapping, and then doing the fix up, okay? And that's pretty much going to get us kind of through that. So that's the takeaway, is like, hey, how do we delete a node at a binary search tree? Kind of apply that algorithm and you're in good shape, okay? So you can kind of practice that stuff on these Quizlet things, or kind of, use your home quiz 4 to kind of study that a little bit, but it's just a basic and good trick to actually use. But we're going to take a look at the code now. It's not on any test, even though the algorithm will be, but I just want to show you, it's nice to see it working. So I'll try not to, put you guys to sleep with this next part. But remember that we're going to delete a particular value, right? And we're starting at some place, probably the head, and we're passing in an additional piece of information now, which is going to be, hey, what's the address of this data member so that we can change it from beneath, right? So remember, if I'm getting rid of the 21, I got to reach back and be able to delete that, okay? So if start is pointing to the 21, I want to know the address of the pointer that got me here. And that's what our start PTR is going to be for us. And that's what's going to allow us to reach backwards without having a double pointer buried in our data structure. Okay, so there's our start. We got our start pointer. And now we can do a little bit of fix up to actually change that. So start is us, this node. Start pointer is not the parent node. It's the data member that's holding the address, okay? So we can say what's at start pointer gets start right, okay? So that's me saying, hey, reach back over here and point that address at the same thing that I am pointing to, okay? So we're doing a little bit of pointer fix up. And for those of you who are a little bit maybe refreshing your pointer logic, this says go to where that pointer is and update its value. So go here and update its value with this address, okay? Which is pretty cool because I don't know whether I'm the right child or the left child of my parent. I have no way of knowing that. But if you give me the address, then I can just go there and update that location, okay? Update the location of how I got here, okay? So, and then we can go ahead and delete that node. And now we've kind of gotten that thing pulled out of the middle of that linked list there, okay? So for those of you in homework 3, we were kind of tracking one thing before we got there. That's a different strategy, and that's okay. This one, I took the additional step of just passing along the address. Okay, so I created an extra argument to the recursive algorithm, essentially, okay, to kind of get me through that problem. So this is all optional. I'm just going to pull up some chunks of the code here rather than go through all of it because we got a lot of more stuff to cover. But essentially, we do our usual kind of pointer fix up. We got to see if we can find the node. So if we're in a recursive situation, we're working our way gradually down the tree, right? So we're calling. If this thing is equivalent to what we're looking for, then we know we found it and now we have to delete it. But fortunately, we have the address of what's pointing to us to allow us to do that, okay? So the idea is if I have no children, that's easy. I just update the pointer that points to me and I delete the node and return true. That means the node is gone, okay? If I have children and I only have one child, then it's almost as easy. I just delete the start node and pull up the non-null child and fix the pointer, kind of the way we were just seeing on the previous slide. So we're either going to do that with a left child, we're either going to pull up the left child or pull up the right child in case number 2 and fix up the pointer. And we kind of saw that on the previous slide. Case 3 is the recursive case. So if I have 2 children, then I just got to decide, okay, which direction do I recursively go? Do I go down the left branch or do I go down the right branch? And it kind of depends on the value I'm looking for, right? If it's less than this, less than or equal to that, we're going to recursively call and go down the left branch. Otherwise, we're going to recursively call and go down the right branch, okay? Now, if we didn't find it, right, at all, then we're going to recursively call, again, follow down the appropriate branch, left or right. Okay. I hope I didn't misstate that. So I feel like I just described that instead of that. So apologies for the confusion there. Let me clear up some of my code. So here's just a quick peek at deleting the start. I won't, again, this is all, you don't have to, follow or, implement this code. Maybe unless you're, going to go implement the binary search tree for your homework 4. But we're basically saying, hey, no children, right? If the left is null and the right is null, then if we're not at the head, then go ahead and just nullify the pointer that we need to fix up, right? And then otherwise, just make the head null, because I have apparently just deleted the last node in the tree. Okay, so that's our case 1. Okay. Case 2, we're just saying, okay, the left child is null, so that means we need to pull up the right child. Okay, so we're going to say, okay, the thing that points to me is going to be what I'm pointing to on the right, because we're not at the head. But if we are at the head, well, then the head is just going to become what's on the right of me, and then I'll delete myself before I return true. Okay, so that's our case 2A. And case 2B is just doing it on the other side, the left side, right? So here we're pulling up the right child because the left is null. And over here, we're pulling up the left child because the right is null. So it's pretty symmetric code here, okay? If I haven't screwed something up. Okay, so those are just part of the code that's there. The last part, case 3 expanded, is if we have to delete the start, right? This is where we find the minimum node. We keep track of the address of the parent pointer, swap the value. So we're just talking about that algorithm a minute ago. And if the minimum node has the right child, then we're going to go ahead and delete it, fix up the pointers, and return. Otherwise, the minimum node can only have one right child, and we're going to pull up the right child in that case. Okay. So a lot to digest there, but that's the kind of a code flyover, if you will. And we're not trying to get you to, learn the code, but you may find it interesting to pull up the solution link for this and try it out. So the solution link is here, which you can pull up and kind of see. And let's just look at it, because I think before we kind of leave this behind us, because I think it is helpful to see it in action. So if I say, okay, I'm going to run this thing, and I say, first off, let's enter some values. I like kind of entering high, low, or low, high when I build my tree. So I'm going to go 2, 8, 3, 9. So I got a little bit of a tree here. So this is the 1. It has no child on its left side. It's got a 7, which has got a 2 and an 8, etc. So if I were to delete the 1, the smallest one on the right side is going to be the 2. So the 1 and the 2 should swap, right? And then we should be able to delete the 1 and pull up the 3. So let's see if we can do that. Let's say -1. Okay, so delete the 1 here should end up swapping the 1 and the 2 and pulling up the 3. So let's see if that actually happens. Okay. So, I got it wrong, actually. Something else happened. I deleted the 1, and that pulled up the, did I have that right? Yeah, I had that right. This was the 2. So I deleted the 1, pulled up the 7. I still have a valid tree, but it just did it the other way. So, gonna have to go in and take a look. It did do. I was trying to delete the 1, right? And thinking that I would pull up the 2 into that position and move the 3 into the 2's position. But doesn't seem that that is what happened. But I still got a valid binary search tree, right? So I still have a 7 at the top, 2 is less than that, 3 is greater than the 2, and the 8 is greater than 7 and the 9. So unless I was misreading my tree here, 8, 1, 2, 1, 2. Huh. All right. Sorry about that, guys. Well, I might be just misnarrating what happened there, but we should have pulled up. Let's just see if I can check. So this is the smallest on the right side of the one. It's got a 3, which means we would delete this, pull up the 3. Interesting. 173. That would have been a valid tree structure. So I may have to go back and look at my implementation of this. Maybe I did something a little bit non-standard here. Okay. I might have pulled up from the left side instead of the right for some crazy reason. Okay. But that's kind of how how complex these things are, right? You can look at it a couple times and not quite get it all right. But that's our algorithm. Uh, Probably the key slide takeaway for remembering all this is this summary here, right on this page. Where did it go? Boop, boop. So you want to focus on, where did I put that? Sorry, kind of jumped past it here. Thought I had a really good summary slide on this. Well, sorry, I've kind of lost my way on that. I think that's what I was looking for right there. Yeah, there's that's the summary on the algorithm that we would follow for deleting that. Okay. All right, so let me leave you with that before I butcher that anymore. And assuming that we've got those things kind of deleted and we haven't broken the tree, let's look on how we go to the next step of rebalancing the tree. Because just because we deleted the node and kept a valid binary search tree does not necessarily mean that it's balanced. Okay. So one of the things we need to know at every node in the tree is how far is it from where we are to the leaf of the tree. And we're going to call that our depth from a particular node. So just to sort of make sure we're familiar with our terminology here. So it's the number of edges to reach the furthest leaf, if you want to think of it that way, from where we are, from any specific node. So the max depth is the maximum of the left depth, right? The left depth or the right depth. So for the 9, the maximum depth is 1, 2, 3, 4, right? So we're seeing 4 on the left side and a 3 on the right. So our maximum depth for the 9 is going to be the 4. Okay. And so ideally, we want to be able to maintain the depth at every one of these nodes so that we can do balancing operations in a moment's notice, so to speak. Okay. So one of the things we want to do is, build this thing recursively, like initialize those values and also represent them in a way when we're printing out our tree so we can kind of tell what the depth is at each particular node. So the notation I chose for our code is just to show the value and a colon and then its maximum depth from that point, right? So here's the 4 depth. This one's a 3 depth. This one's a 2 depth, etc. And you can see, of course, that the leaf nodes should have a 0 depth there. So we start to think of that as just another data member in our node, and that we try to keep up to date at all times. Okay, and I kind of updated our print geeks function from this point going forward whenever we show the tree so we can kind of see what it looks like. So just quick, taking a look back at our node now, we're going to add this balance factor, which we'll talk about here in just a second, and our maximum depth at this particular node. So we have 2 new data members we've got to kind of keep around for the purposes of balancing. Okay. And then we'll always have those things initialized to 0 to start. Okay. So that's our moderately updated node class. Okay. So let's take a look at how we actually kind of update the maximum depth. So each time we insert or delete, from that particular point, we want to update the balance factor and essentially the max depth. But the max depth is the first thing we got to actually do. Okay. So let's take a look at this recursive function real quick. I think I've got it laid out reasonably well, so we can kind of look at it. But let me see if I can pull it up without blowing myself up here. So let me kind of go to Max and find our to-do. Okay. Okay. So basically, when we're getting ready to update the maximum depth at a particular node, we're going to ask ourselves, is this thing null? That means basically we have no links to follow, and the depth at this particular point is going to be a 0. Okay. So that's going to be a 0 depth because we're at a leaf node, or our tree is altogether 0. Okay. Otherwise, we're just really going to ask ourselves recursively, pretty classic questions. What is the answer for going left? And what is the max depth for going right? Start right, okay, like so. And then we're going to add 1 to that to count myself, like the current level of depth, okay? So whatever the max is of my children plus 1 for me gets returned up the stack recursively, okay? And there's my base case. And that's really all we should need to be able to do this. So let me see if I can actually do this one, okay? So I'll add a 1, a 5, a 2, a 6, a 3, and a 7. Let me zoom this back a little bit. And we should start to see our max depth, okay? So we're going down the right side here. We're at a 2, then we're at a 1, and then we're at a 0. So we kind of go this way and zigzag to here, okay? Versus this side, which is a 1 and a 0 there, okay? I know this is not the ideal way to visualize a binary search tree, but that's really where we're going. So having those depths now allows us to sort of assess how balanced that tree structure is. Even though it already is a valid binary search tree, it's just not very well balanced. You can see that the 1 doesn't have any left child over here. It just has the right child and everything else, okay? But that's really kind of a key thing we have to be able to maintain, okay? Figure out what that is recursively. Okay? So assuming we have that information, we have the maximum depth, we're maintaining a valid binary search tree, we can kind of finish the full implementation of these AVL trees. So this is the Adelson, Volinsky, and Landis, or AVL tree that's been around for a while. So there is our max depth at each node. And the way they define balance is by saying if the max depth at each side is no more than 1, a maximum of 1 out of balance, then it's considered to be okay. Okay. So if the absolute difference between the max depth on the left side and the right side of any one node is within 1, 0, 1, or -1, then we'll say, okay, then you're okay. And we won't do any kind of fix up on that. So we're really just calculating the difference between node right arrow max depth and node left arrow max depth, and asking if it's 0, 1, or -1 at every node, right? So it's a recursive definition, essentially, okay? Okay, so in that case, we're in balance, right? Those are 0, those are within tolerance. Okay, these two are within 1, these are within 1, and that's within 1. So we would say that that particular binary tree is balanced. Okay. Okay. So that's our balanced tree. So getting to know whether a tree is balanced according to the AVL rules is the key takeaway for the midterm. Not so much the actual code for doing it, but just understanding the algorithm. Okay. So let's take a look at a few of these things and just test our understanding of that. Okay. So for sure, we don't have to just be balancing binary search trees. We could balance any kind of binary tree. So here on the left side, we have something that is balanced, but not specifically a binary search tree. On the right side here, we have something that is unbalanced, but is a binary search tree. So these two things can actually kind of happen separately, okay? Let's take a look at some worst case scenarios, right? Where if we're trying to find a 5 in a relatively unbalanced search tree, it's pretty obvious why that's a bad thing, right? So we have to travel through 6 edges to find the 5 versus if we could fix that thing up, it's a lot more efficient. So I know we've said that kind of stuff before, okay? So balance will give us the optimal axis. So let's take a look at some examples. So is this tree balanced or not? So we have a difference of 1 here, and then we have a difference of 1 here, and these two are 0. So that one's okay. That's definitely a balanced binary tree, okay? This one here, not so much, right? Maximum depth down to here is 3 versus 1, so that's a difference of 2, so not balanced, okay? They get a little trickier, so this is probably as tricky as it gets for the midterm. So you have to kind of crawl through the tree and check the numbers, right? So where is it not balanced? This is a difference of 1. That's a difference of 1. That's a difference of 1, right? So everything is okay over here on the right side. The problem occurs over here, right? A 1 versus a 3. So there we have our imbalance. And so that kind of breaks the tree, okay? So we just got to be able to spot that stuff to kind of assess whether we're in balance or not, okay? So terminology wise, the depth, right? We're just essentially comparing the depth of the left and right branch at that particular location. Okay. So probably, hopefully I'm not, making it too complicated, but that's all we're really doing is subtracting those two things. And for our convention, we will subtract the left from the right. Doesn't make a whole lot of difference except on test questions. So we got to be pretty consistent about that. So we'll subtract the left max depth from the right max depth to get that balance factor. Okay. Okay. And if they're not out of balance, then we're okay. And just repeat at every subnode. Okay. So we're going to store, in addition to that BF or balance factor. So we'll compute that, store it in the node along with the max depth so that we have it for reference without needing to recursively search down under the tree and figure out what it is. And this extra piece of information will allow us to do local fix-ups on our branches without needing to go deep into the binary tree. Okay. So a couple more real quick before we leave it, right? So at node 13, the balance factor is -1. Right minus left equals -1. Right minus left, -2. Right minus left at 13, that's in balance. Okay. Right minus left at node 9, that's going to be a 2. That's out of balance at node number 9 there. Okay. So those are just kind of our conventions. Okay. Okay. So balanced, not balanced, balanced, and not balanced at those particular nodes. Okay. In particular. Couple more and then we'll let it go. Right. So over here, balance factor at 13, right minus left, 0 minus 4, 0 minus 3 rather, -3. Balance factor at 13, 1 minus 3 gives us a -2. Balance factor at 12, it's going to be 0. So it kind of depends on where we're asking the question as far as any quiz questions go. Balance factor at 10, 2 minus 0, that's 2. Balance factor at 9, 3 minus 1 gives us a 2. Hopefully relatively straightforward. Okay. Not balanced, not balanced, not balanced, and not balanced. Okay. All right, so how do we fix these things? So this is the final wrap up here, or at least for today anyway. So ideally, we want to fix it as soon as we break it. So if we insert something or delete something, we want to check the depth, max depth at that point and decide whether it's time to do some fix up, okay? And so, and we can't do that fix up and break the binary search tree. So we have to do it with this technique called rotations. So tree rotations are a little strange at first. So we are relinking the pointers, and we're doing it in a very specific way with just the children in the area of the change. Okay. So we're going to fix usually one or two pointers at a maximum, and it should fix all of the rest of the tree above and below us. That's the goal. Okay. And it should not break our binary search tree if we do it correctly. So there are two kinds of operations that are pretty standard for the AVL tree, the rotate left and the rotate right. So the rotate right will show you as kind of a clockwise rotation. So if you take, your hand and you rotate your fingers in the direction of the clock, it's sort of rotating over the top to the right. And if you rotate with your left hand toward the left, sorry, if with your right hand toward the left, you're going to rotate it in a counterclockwise. So I didn't pick these names, but this is kind of what they're called and what they mean. So if I tell you, hey, we got to rebalance this tree here at node number 4, I want to restructure the tree so that it is no longer out of balance at node number 4, but I don't want to break the binary search tree. So the way a rotate works, we want to pull the 2 up and push the 4 down, and then hand the 3 over like a football, right? So we're going to be saying pull the 2 and the 1 and the 0 up, pushing the 4 and the 5 down, and then transfer the 3 across, okay? And we're sort of moving that 3 from being the largest thing on the left to now the smallest thing on the right. And that's how we actually kind of manage it to keep the the ordering of the tree correct while fixing the balance. Now notice that there could be an infinite amount of, not infinite, but there could be a huge tree under here, and there could be a huge tree under here, and a huge tree under here. It really doesn't matter. We're doing a local fix up that's going to shorten the depth on this side and lengthen the depth on this side. And that's how we're fixing the balance through that kind of rotation there. Okay. So, but we really only just have to focus on the changing of the links that you kind of see there as part of that rotation. So that's what we call the right rotation. And the only real tricky part is that the 3 transfers from the left side to the right side. Okay. Comes across like that. Okay. No longer can be part of the 2. Okay. The left rotation, as you might expect, the 4 is going to become the new root. Okay. We're going to push down the 2 and the 1, pull up the 5 and the 0, hand the 3 back across so it becomes the right child of the 2. Okay. So that's our kind of fixing something that's too heavy on the right side. Okay. And so incidentally, we would kind of call this a right heavy. If I were to say, hey, we got a right heavy over here, we're going to pull that thing up and balance that thing out, along with all of its subtrees that are going to happen as well. Okay. So those are our fundamental rotations. So we sort of can see it this way. This is a handy GIF that I found on Wikipedia that kind of shows what we mean, right? So left rotation takes that inner tree and transfers it over, right? Right rotation takes the inner tree, transfers it the other direction, okay? And that makes one side shorter or longer, depending on which one we're doing, okay? So I will have this animation in your quiz questions and for your midterm to help you kind of visualize this, because I know it's kind of hard to see when you're kind of new at it. But most of our questions will revolve around this, the idea of this operation, not specifically the code, okay? So let's just do a couple real quick. So if I were to say, if I want to rotate left at the 2, we're going to push the 2 down and pull the 5 up, transfer the 4 across, okay? So we got to try to visualize that before we see the answer, right? Push the 2 down it takes the 1 with it and then pulls up the 6 and the 7, and we just hand the 4 over to the other side. And the 1 and the 0 doesn't change, right? 0, nothing above us changes except for our linkage to that 0. Okay. So that's a left at 2. Okay. A left at the top node, if we just try to visualize the numbers, right? So if I'm rotating left or counterclockwise at the 2, I'm pulling up the 4. So the 4 is going to become the new root. The 2 is going to go down, right? So 4, 2, 4 pulls up the 6 with it. Okay. 6 pulls up the 7 and the 5, right? And the 3 gets handed across. Right? And that brings us back into balance. That was our tree that we had. Okay. A couple more. So here we've got something. We're going to do a left counterclockwise at 2. This one's a little bit different. So 2 goes down, 4, 6, and 7 get pulled up. So 4, 6, the 1 gets pushed down under the 2. 5 gets pulled up, and there's nothing hanging off of the 4 that needs to get transferred over. This is usually where we get some mistakes on quiz questions, okay? As we get the 6 being assigned over on the left side there, for example, okay? All right, couple more. So we're going to try a left counterclockwise at 1. So this is possible. So we're going to pull up the 4, push down the 1, hand over the 3, 2. Okay. So the 4 comes up, 1 goes down, 3, 2 comes across, and then the 6 just pulls up its left and right children. Okay. That's our left rotate at the root. Okay. For fixing balance. 1 or 2 more. Right rotate at 7. So not the 0, but right rotate at 7, pulling up the 3, pushing down the 8, handing across the 4, pushing down the 7 and the 8, handing across the 4. Okay. And now we've rebalanced our tree. Okay, almost there. Maybe the last one here. So if we're going to rotate right counterclockwise at 4, now, I'm not saying this is necessarily fixing balance here. This is just, let's just do this one, right? So we're going to pull up the 2, push down the 4, the 6, the 7, and the 5, and pull up the 1 along with all of its subtrees, right? And hand across the 3 with all of its subtrees to the 4. Okay. Okay. And then rotate at the top at 4, push down the 6 and the 7 and the 5, pull up the 2. There you go. Okay. All right. And just keep in mind, all of those children can be, can go on and on and on. So you can be in the middle of the binary search tree when you're doing this, and it will still locally fix the balance. Okay. And then the 2, 3 comes across. So if we keep those operations live while we're doing insertions and deletions, our tree always stays more or less in balance, which keeps it close to that log base 2 kind of search behavior. So that's our real goal for doing all this fix up. Okay. Now, if somebody hands us a tree and it's just completely busted, we can traverse it in order traversal, build a list, and then just like our binary heap, we can take that list or that array and then kind of reconstitute the balance tree from the in-order traversal. So we could use that array to actually build the tree from scratch, assuming that it was already out of order. But ideally, we kind of keep stuff cleaned up as we go. And that's really what the AVL tree does for us. Okay. So next time we'll kind of look at a little more code and the sort of more complicated combination rotations. But we're going to pretty much wrap up our discussions on the binary search trees in about a half a lecture. And then we're going to take our first dive into asymptotic analysis, which is really more of the math language of algorithms. So we've talked about worst case analysis or best case or average case. So we're going to relate that common language to the more formal math language of big O, big omega, or what's called big theta. And we'll dig into some of that, but we're not going to go super, super deep into the math. But we all want to be able to understand this because it's the language that people speak when they talk about analyzing algorithms. So we'll try to give you a little more foundation on that next time. Okay. And that's that. And we do have a lab today. Bear with me here while I check this because I don't know why I forgot this, but I thought we have a lab today, but for some reason I don't have that in my slide set here. Lab 13 is not available. So I think you guys get a pass, actually. If there's no lab, then there's no lab. So I'm not going to create another one for you. So somehow that escaped my attention. So no lab today. We'll let you guys focus on your homework if you're doing it and your quiz, and I'll see you on Thursday. Okay. Thank you. Let me kill our recording here, and then I'll come around and answer questions.
Right,
okay.
thank you.
Thank you. Have a good week.